do our next thing here. I'm gonna, let's go ahead and do this one real quick, just as a practice. Let's find the domain, but let's not do all of them. Let's just do here, I'll circle the ones that if you want to do them all, go for it. I'm not going to stop you, but in the interest of time, let's just look at a couple of them. So we want to find the domain of these. I'm going to do I'm having trouble with this thing today. I'm having a lot of trouble with this thing today. I'm going to slow down for a second. Okay. Let's do A, C, and E. We could briefly touch on the other ones if we want to or something. So let's say finding the domain of these three different functions. And I'll give you a minute to kind of get ahead of me here. Thanks, guys. If you just joined recently or you've forgotten to do it, make sure you put your first and last name in the chat for attendance, okay? So discrete, we have actually an example of a discrete function here, A. A is discrete. There's a countable, actually a finite, a set number of inputs and outputs. This is a discrete function, just a set of points. The domain are just the inputs, right? So the domain is just going to be all of my different inputs, and looks like they're already in order. Usually we would want to write them in ascending order if we can. 0, 2, and 4. So this would be our domain for the first one. Just the x values, right? I'm just talking about the x's. And I think I got them all. For C, we have that fraction issue. We have a variable in the denominator of a fraction, right? Anytime we have that, we need to make sure that our fraction will never have a 0 in the denominator. Well, there's one obvious value here that x can't be. X cannot be -5 in this case. If that happens, then we get a 0 in the denominator. If this was something more complicated, we might have to set our denominator equal to 0 and solve that equation and figure out what value or values might be an issue. But in this case, it's a pretty easy one. We can just kind of see it. Last one, we have a radical. And again, we can't take the square root of a negative number and get a real value. So we want to do this. We want to take what's on the inside of that and set up an inequality. We want it to not be negative. So the way we say not negative is it has to be greater than or equal to 0. And then we solve this inequality. This does have a bit of a trick here because the coefficient in front of x is a negative. We'll need to remember how that's going to affect our inequality symbol. So I subtract 4. And then I'm going to have to divide by -3. And anytime we have to do that, we have to flip the inequality sign. So it's actually going to be x is less than or equal to 4/3. So this is our domain written using an inequality symbol, less than or equal to 4/3. We could also do that as an interval notation. So we could say our domain is from -∞ all the way up to 4/3, including 4/3, because I have that or equal to. So I'd use the square bracket. So this is interval notation for that same inequality symbol. It's maybe slightly more complicated, but we'll be using interval notation a lot. So these two things are communicating the same information. If x is less than 4/3, that means it's going to go all the way down to -∞. There's no bound on the lowest value it could be. Any questions on this one? So really quickly, just touching on these two. B is actually pretty easy. There's neither of these two issues. There's no denominators. There's no square roots. So this one would just be all real numbers. Or the other way we could do it is from -∞ all the way up to infinity. So every number doesn't matter as long as it's a real number. Volume of a sphere. So if this is a function, the volume is a function of r. So what values of r would not be allowed? Any ideas for that one? I mean, technically as an equation, I could put in anything I want, right? I could put in 17, that's a fine radius. But what if I put in like -10? Would that make any sense? If I had a sphere with a -10 radius, right? So negative numbers don't make any sense. 0 is kind of debatable. A volume of a sphere with radius 0 would have a volume of 0. It kind of just means the sphere wouldn't exist, but I suppose that can work. So you could argue whether 0 is included. I'm just going to say that it's greater than, that the radius has to be greater than or equal to 0. That's one way to talk about our domain. Negatives clearly don't make sense, having a negative radius, because a radius is a measurement of length. We don't really talk about lengths in terms of negatives. So that's one way to express that one as a domain. Now, we weren't told strictly which was the x variable, the independent variable, and which one was the y, but generally it makes sense that it's solved for the output and the input is over here in the equation side. Some people would write it as like v of all, the volume with respect to the radius is equal to, and then that formula just to more clearly define it as a function with an input and output variable, but it doesn't really matter. Okay. I think I'll get this at some point. All right, so the difference quotient. This is the last thing that we didn't get to from 1.1. So the difference quotient is this thing right here, f of x plus h minus f of x, all divided by h. So the difference quotient is used to calculate the derivative when you get into calculus. Really, we're just going to, it's a weird way to kind of work with functions and plug in an expression x plus h into a function and do some algebra with it. And to kind of get comfortable with the idea, because when you start to take a calculus class, you'll need to do this process to create a, to find a derivative, at least in the beginning until you learn some of the shortcuts and such, because there are a lot of shortcuts for derivatives as well. Really what's happening here is you're taking a function at x and you're adding, for a derivative, a very infinitesimally small amount, and it's kind of just a way to calculate slope. That's what derivatives are all about, is calculating the slope of a function. We won't get into that too much until later on when we learn more things about limits and such. Right now, we're just going to practice evaluating the difference quotient and kind of bring it in more as an exercise of functions. All right, so let's take this function right here, f of x equals negative 5x plus 3, and we're going to figure out what the difference quotient is. So f of x, that's just this. That's just the original function, negative 5x plus 3. F of x plus h, well, that one we're going to have to figure out. We're actually going to have to plug in x plus h into our function and do a little algebra with that. So I'll kind of get things started a little bit. Okay, so I have my difference quotient. I'm subtracting the original function. That's kind of the easy part to start with. So I'm subtracting the original function. That's this piece. I want to figure out what f of x plus h is. Well, that would mean plugging in x plus h into our function here. So negative 5 times x plus h plus 3. Right, I just basically took my function and plugged in x plus h. And for the second piece, I just rewrote the function rule, f of x, which is that. And that's all going to be divided by h. Now, the idea of this is that at some point, we're going to be able to simplify this enough that h actually is just going to go away. We're going to be able to get it out of there, ideally. So let's see what happens here. So I'm going to distribute. I'm going to distribute. I keep clicking the button on my pen and it messes things up. Okay, so we get negative 5x minus 5h plus 3. Over here with this subtracting this whole thing, so I'm going to distribute this negative on the outside here. So we end up with plus 5x minus 3, all that being divided by h. So on the top, you can probably see there's some things that are going to cancel out or at least simplify a little bit. So I have negative 5x and positive 5x. Together, those make 0, so those can just go away. I've got positive 3 and negative 3. So those can also make 0 and just go away. And so the only thing I have left on the remaining on the top is this, negative 5h over h. And then, obviously, and just like we hoped, the h's cancel out, and the derivative of this function is actually just negative 5. Which should kind of make sense here if you knew what a derivative was. A derivative is the slope of a function at a particular value. Since this is just the equation of a line that has a constant slope, negative 5, I expected this to be my answer, because no matter where I'm at on that line, the slope of this graph is negative 5. It's a little more complicated if our original function is a curve, right? If it's a curve, the slope is going to be changing as it curves. But since this one is a line, the slope is always the same. So we end up with a constant. Yeah, that only works for linear equations where we actually have a constant slope. Every other function, because they curve in some way, with some exceptions, absolute values aren't really curves, but yeah. So we end up with a negative 5. Anyway, the idea here isn't to understand that piece. I'm just kind of filling it in so that hopefully it, as you hear it later on, will make more sense. The idea is working with a function and being able to evaluate a difference quotient. So let's do a harder one that's not just a linear equation. Still getting the hang of this. Okay, so here we go. Second example, we got a quadratic equation. F of x is equal to x squared minus 4x plus 7, and we're going to evaluate difference quotient again. So I'm gonna write it all out. Feel free to get ahead of me if you want. Okay, so for the first part, I'm plugging in x plus h into my function. Okay, so that's that f of x plus h part. And then I'm going to subtract my original function, f of x. And then h on the bottom. So you can see that as the function becomes more complicated, defining this f of x plus h part is just going to get a little bit harder. There's going to be more algebra, more like multiplying and combining like terms and simplifying and stuff. But this shouldn't be too bad. So when I multiply this one out, you could kind of do it on the side if you want to. You could figure out x plus h times x plus h. That's x squared plus xh plus xh plus h squared. And then combining those two, we get 2xh plus h squared. Since it's squaring a binomial, there is kind of a pattern you can always learn about. You're always going to get this squared and this squared. That'll be the first and last. And then you're just going to get 2 times the product of those two terms. So those two terms multiply together to give me xh, and I'll always end up with 2 of them. So you could remember that as being a little bit shorter, but it doesn't matter. All right, write that out. And then I have to distribute this. So that's a negative 4 for my distributing purposes. I'm doing negative 4 times those. So negative 4x minus 4h plus 7. And then I need to distribute this subtraction to this entire polynomial here. So that's minus x squared plus 4x minus 7. And all of that is over h. I'm going to change the color just because there's going to be a lot of stuff that cancels out. So hopefully there's a lot of stuff that cancels out. So I've got x squared here and negative x squared here. So those together make 0. Get rid of those. I have, let's see, minus 4x and 4x. Those can go away. I have plus 7 and minus 7. Those again make 0, so those will go away. Okay, so that's pretty convenient now. What I have left are these 3 terms, and there's nothing I can really do to put them together. That none of them are like terms, right? xh, h squared, h. Yeah, none of those are like terms. Doesn't really matter the way I do it. Let's just write it the way they are. 2xh plus h squared minus 4h divided by h. So really close here. We can go ahead and divide this h through because all of these 3 terms have an h in them. So if I divide an h through everything, I end up with 2x. I'm going to reorder things a little bit, 2x minus 4. So I want to put that one second, and then plus h. And so this one is close. This is really close to the derivative. In the technical derivative definition, we would think about this as h goes to 0. So if h approaches 0, this term doesn't have any value anymore. It just becomes 0. But in the original definition, h can't be 0 because it's in the denominator. That's a kind of a nuanced weird thing. But here it's okay if it's 0. So once we simplify, it's okay. So this would be our derivative. We don't need to know that though. This is what we're looking for as our final answer. The order of the terms is also not important. It doesn't matter if you rearrange these terms as long as you have the correct values and the correct signs with them. So that's a difference quotient. It's really just an exercise in evaluating functions, combining like terms, and doing a little bit of simplifying. Again, the more complicated the function, the more going on that you have to figure out. Okay. All right, so this was the homework for the first section. As far as homework goes, I'll just take a second to say this. I'm not going to be collecting your homework. What I'm going to do is I'm going to give you a quiz at the end of the week that has some of your problems in it. And some of the problems from the homework in it, kind of a mixed short quiz. And so you can use your homework to help you with that quiz. The idea is you need to kind of hold yourself accountable for doing as many of the problems as necessary for you to understand this. If that means doing all of them every time and asking questions about all of them, fine. If that means doing 75% of them, 60% of them, whatever you need to do to make sure you understand this stuff. It's a lot of more responsibility in terms of that. I just don't have a great way to be able to quickly look over your work. Doing it on the computer is so tedious, but I will be able to look at things you do on the quiz. I'm going to ask you to type some things out with like explanation a little bit to give you feedback there. And I am going to run a homework, like an office hours session if you do want to come by and get help from me specifically on problems. All right. I'm going to move on to 1-2. I'm not sure how far we'll get. We have about 10 minutes right now. Okay, 1.2 is focusing a lot on the graphs of functions, and graphs are all over the place. Some people like graphs, some people hate graphs, but a graph is really just a visual representation of all the possible input-output pairs that a function has, right? So in this case, it's a continuous function, so our graph is actually a smooth line, not just a bunch of points, because really every single place along this curve of this parabola is technically an input and output pair for this function. So even like right in here in between -2 and 3, whatever, there are an infinite number of values in there that we could pick that are input output pairs. And because there's an infinite number of points, it makes a nice smooth curved graph. So up here we have an example of a particular input-output pair. If you plug in 3, you're going to get out 4 for this particular function. One thing we're going to be talking about is domain and range. So on a graph, domain and range can be difficult to interpret, easy to interpret. It really depends on the graph we're looking at. So here we have a graph that wasn't supposed to be there already, but that's okay. So this is a weird graph. It's got some endpoints on it. Sometimes graphs have endpoints with open circles like this one and closed circles like this one. An open circle means the graph is not defined at that particular point for some reason. Now that might be based on the equation. Maybe if you plug in -3, you get a divide by 0 or something. Or maybe it's just chosen to be restricted in this way for some reason. Maybe the number, any number smaller than -3 just doesn't make sense for the context of the problem. There's lots of reason to restrict a graph. And then here, we end at 1, at x equals 1, but the closed dot means we do include that point. So 1 is part of our domain based on this point, but -3 is not because it's open. So when we're writing domain and range, we're going to be using interval notation a lot. Whenever you have open endpoints there, we're going to use parentheses because the function's not defined at that particular value. Be careful because the x value might not be defined, but the y value might be defined at a different place on the graph. And closed dots means we use brackets because the function is defined at that particular value. So our domain here is from -3, not including that value, to 1, including that value. So it looks like that. -3, not included. We use parentheses there. 1 is included. We use a bracket with that. Now the range, this is a little tricky. People often do get this one wrong. They do the order of it wrong. You want to use the smaller number first, the bigger number second. But they also look at this right here and they say, it's not defined at this value. It's not defined up at 0. Okay, it's not defined at 0, but it is defined at 0 right here, right? So the output values, it might not be defined at the end of the graph, but you need to look and be careful because that end of the graph might not be all the places where it is, right? So our lowest our graph goes is -4, and it is defined there. And the highest our graph goes is 0. And again, it is looks like it's defined at 0 based on that. So we end up using closed brackets for both of these. So you got to be careful when you're looking at the graph and making sure you're paying attention to the open circles, but also if maybe the graph is defined at that number in some other place. I like drawing these lines with the dots and the open circles. That kind of helps me visualize it, but it's certainly not necessary. Okay, here we have 2 other graphs, and I want to state the domain and range for these. So go ahead and look at them, see if you can figure out the domain and range on these 2 graphs. So for me, I'm seeing my domain this way. This is the farthest left my graph is, the smallest x value that it takes on right here. Open circle because we're not including it, but it goes all the way up to it, so -3. And then 2 is the farthest right, the highest x value that it goes. Again, not including it because of the open circle. So that should be from -3 to 2. For the range, the lowest value that I have appears to be 5, and it does, or sorry, -5, and it looks like it is defined there. And then the highest value, or at least the one that it approaches, is all the way up here, and that's an open circle. There's no other point on the graph. It's open there, and that's at 4. So when I'm writing my range, it should be from -5, including it, to 4, not including it. So I think that's what it says. Okay, yeah. So from -3 to 2, not including -3, not including 2. And from -5, which we do include, up to 4, which because it's not technically defined there, we don't include that. And for our second one, take a second, see if you can figure out this one. It has something that we haven't really talked about with this yet, but I think you've seen it before. So looking at my domain, my smallest x value is 2, but I don't have a biggest x value. It keeps going to the right forever. So I want to use infinity with that, right? It goes from 2 to infinity. For range, similar idea. Oh, I'm sorry, it's not 2. I'm talking about x values. It goes from 0 to infinity. Domain are the x values. Easy to get that mixed up. I even misspoke already. So the x value is what I'm talking about for domain. So it goes from 0 at my x value here all the way to the right forever, so to infinity. And for my range, my lowest point is at 2. And my highest point, well, since this graph is kind of going slightly up forever, it is going to be going up to infinity. It's going up forever. So that's what we should see when we write that domain and range. So my domain is from 0 to positive infinity. You can just write infinity, or you can write a plus to indicate that it's positive infinity. You don't have to write a plus for positive infinity. It's kind of implied. But if it's going negative infinity, you do need a negative sign in front of that. And our range, our lowest is 2. And again, it's going up forever, which is positive infinity. All right, we have 1 minute. So clearly we didn't get through everything. I'm going to stop this in the interest of not going too crazy with this. So on the Google Classroom page, I did put up the homework assignments. So I'm just going to bring that up really quick just to share with you guys. Perhaps it will load in time. It looks like it is. We're going to finish what we can tomorrow. Again, I'm still trying to get a feel of how much we can actually get through. I reorganized our classwork tab. It's got textbook here, week 2 instructions. If you click on that, it has the homeworks that are there. And I am going to post a quiz on Wednesday, though I might make some modifications based on what we've actually gotten through. Don't freak out about it. We're going to, I'll adjust as we need to. And also I have the notes, link to the notes that you can get to that, the slideshow that I've been showing you guys, and a video of yesterday's lesson, and I'll have a video of today's lesson up there if you want to look at it. All right, go ahead and go to your next class. I'll see you guys tomorrow.
See ya.
Bye.